Thank you very much. That was the best introduction that I could ever hope to pay for. That was brilliant. Thank you. What I really like about this conference is this theme of redefining tech, redefining technology, because that pretty much is what technologists have to do. If we're not building on the things that we've done before, if we're not kind of progressing the state of the art, then perhaps we're kind of failing as technologists. Perhaps we're not doing the best job that we can with the tools that we've got, and frankly the privilege that we've got to be in a position where we can do these things. But sometimes we kind of redefine these things to our own detriment as well, and so I think I kind of took a different interpretation and a different understanding of this phrase, redefining tech. And that this is a topic that I've been kind of researching for a few years in various contexts. I think that what often happens is that like some great idea gets introduced, and then we come along and we think, well, this I can see what you're trying to do, and it doesn't quite match the way that I think about things or the way that I work. So I'm going to take the bits that I understand, and I'm going to call it the same thing. And so we get this kind of Humpty Dumpty thing. Lewis Carroll in Alice's Adventures Through the Looking Glass, or Alice in Wonderland as people also call it, said, when I use a word, it means just what I choose it to mean, neither more nor less. And I see this happening like over long time spans. Sometimes, so the examples that I'm going to look at today are over like the time of a few decades, and sometimes this is good. Like evolution in the way that we think and building ideas on top of other ideas certainly has value and helps us to increase our impact and increase our capability as technologists. But sometimes things become more complex for the sake of increasing the complexity, or because the small kernel of the idea that we originally came up with didn't quite make sense. The conceptual leap to get from where we are now to what we're being told is so big that we kind of settle for somewhere in the middle that is actually kind of harder to work with and harder to think about. And when we do that, we dig in the trench here and go, right, this is the position that we're taking on this. Wow, this is really hard. We're going to give up on this now because that didn't work. Whereas maybe what we can do is look at what was it that the people who introduced this were thinking about when they told us about this idea. If we try and empathize with those people as designers of ideas, as inventors, if we try to think about the problem in the way that they were thinking about it, does this help us to understand the solution that they came up with? So, an example from kind of close to my experience is that there's a guy called Ward Cunningham, and can we have a quick show of hands, people who have heard of Ward Cunningham? Has anyone heard of a wiki? Yeah, there's a few more hands going up for a wiki. Ward Cunningham was the person who invented the wiki. He was also the person who invented design patterns. He was one of the agile signatories. He's one of the kind of big thinkers in software engineering. And he had a colleague who's a guy that I've worked with in the past called Kent Beck. Have people heard of Kent Beck? So Kent Beck famously reintroduced test-driven development. This was an idea from the 1960s that people had forgotten about, and he said, hey, it turns out that writing our tests first is a good idea. And the way that he describes much of his career is that he follows Ward Cunningham around and when Ward Cunningham has a good idea, Kent Beck says, yeah, what Ward meant was this. But then I've also worked with a guy who organised the NS Scotland series of conferences and the Scottish RubyConf, a guy called Alan Francis, who worked with Kent Beck, and he describes kind of following Kent Beck around and saying, right, so what Kent meant when he said that was this. So we kind of see this telephone game of people like reinterpreting ideas and perhaps changing them along the way, sometimes for the good and sometimes for the bad. So object-oriented programming is a great example of this, and this is a pet peeve of mine. Is that this quote from Alan Kay from I think his 1997 OOPSLA keynote. He says, like, I invented the term and I didn't mean C++, but C++ was kind of state of the art in OOP at the time. Java was absolutely brand new. And he worked on the team at Xerox PARC, who, again, didn't create the concepts behind object-oriented programming. What they did was kind of distilled them and learnt from people who had been doing this before, with programming languages like Simula, or even just tape loaders, where the first block of the tape had the name of a function and then the address of the function implementation. So you could choose at runtime to go to a different location on the tape to use the same function just by rewriting this block. And they distilled it down to like a few simple concepts that they embodied in the Smalltalk programming language, and they iterated Smalltalk over over at least a period of a decade, throughout the 70s and then into the 80s when it became commercialized. The goal of Smalltalk, or one of the main goals, was to make programming personal and accessible to children. So the people who invented the integrated concept of object-oriented programming did it so that small children could learn about problems by modeling those problems on the computer, and could also learn about the computer while they were solving these problems or adapting them or extending them. So 1970s object-oriented programming is simple enough to teach to like 8-year-old kids. 2010s object-oriented programming, 20-teens, whatever we want to call this decade, object-oriented programming now is so complex that we professional programmers have all flipped our desks and gone, right, we're going to find functional programming, because like learning lambda calculus is easier than doing object-oriented programming. Or we're going to do protocol-oriented programming because learning about abstract data types is easier than doing object-oriented programming. Now that complexity has to have been introduced somewhere along the path, right? It's not that we as I'm imagining most of us in the room are adults. Maybe there's some children, that's fine. But we, as largely a group of adults, presumably are not less capable at thinking than 8-year-old children were in the 1970s. It's that we've added a load of complexity and bloat and just mismatches between the practices that we have and the thought processes that we are using, and have made this thing more complicated than it needs to be. So if that's true, what's to stop functional programming collapsing under its own weight in the next couple of decades? Because we already had like the first functional programming revolution decades and decades ago, when people were using Lisp and all sorts of languages. Lisp was very common in the first AI explosion. Then there was the AI winter, and people stopped using Lisp unless they used Emacs as their text editor. So we've already seen functional programming die off because we weren't getting the results that we wanted out of it. What's to stop that happening again in the same way that it's happened to OOP? Taking a small example from even within that. Here are two diagrams that both describe the model view controller paradigm. And you can tell that because they both have 3 boxes. One box says model, one box says view, and one box says controller. But the collection of arrows between these boxes is completely different in each of the 2 cases. The top one is it's adapted from some documentation created by the Smalltalk team once they were commercial and had a company called Park Place. And the second one is the Cocoa, the Apple developer documentation description of MVC. Now, what this means is that if I have 3 boxes on my diagram, I have an MVC architecture. So I can claim to be doing like MVC, and I can say I have like got this this pattern, this architecture that comes from this long heritage of like thinkers like Alan Kay and like the experts at Apple and all of these people, and all I've had to do is find 3 boxes in which to put the bits of my software. I haven't had to do the same thinking that led to like MVC the way that Smalltalk works, or necessarily even MVC the way that it works in Cocoa. So I'm not saying like we have to stop evolving our ideas. I'm not saying we're like down with this sort of thing. Let's not change what we're doing. What I am saying is like let's be a bit more kind of considerate and empathetic when we see an idea that we think this looks like a useful thing, rather than going, I'm going to just take the practices that I see these people doing and I'm going to adopt those practices. We need to be a bit more critical both of those ideas and self-critical about our own mindsets and about the things that we value and the ways in which we think about problems, and ask ourselves, does this collection of practices match with the way that I think about about my work, about my craft? Does the person who said this come from the same position that I do, or did they have a different problem to solve, or were they thinking about things in a different way? Rather than adopting their practices, should I try thinking about the problem the way that they were thinking about it? Should I try to find a different way to achieve what they are able to achieve, because our kind of design vocabularies, our mindsets, our contexts, whether it's historical context or like platform context or whatever, are just so distinct that these two things are going to be irreconcilable. So that's the real thread of this talk, and now I'm going to use a particular kind of worked example to show you what I mean. The solid principles were, well, the word solid was due to Michael Feathers, but the concept, these 5 design principles in object-oriented programming, were first kind of grouped together as a collection of commonly useful principles by Robert Martin in the year 2000, and he came up with these 5 principles, but just put them in a different order. And then Mike Feathers said to him, you realize if you put those 2 in the other order, then you'll have the word solid as an acronym, and that will like help people to memorize these things. And so they did. They reordered these 5 principles, came up with the word solid, and now plenty of people have heard of them. So I've now used the word a ton of times, but if you think back to before I did that, how many of you had already come across the solid principles? That's like a load of hands throughout the theatre. And presumably, like those of you who could rattle off the names of the 5 principles. But like, how useful are they? Are they this kind of grandiose architecture that's like stable and lasts for centuries, or are they castles built on sand that are going to crumble away? Well, we can ask that question of each of these 5 things. For example, the single responsibility principle. My workflow manager class might be a single responsibility, while you might think get and set on the same thing. Aren't those 2 different tasks? We don't necessarily all agree on what a responsibility is. The dependency inversion principle. If I do that twice, if I invert then invert, aren't I back to where I started? That is this helping me get anything done? And like kind of pithy jokes and snark aside, like there obviously are some ideas that resonated with a lot of people, and there's also like a lot of kind of confusion about how to follow these things. So the title of my talk hopefully kind of trailed to the fact that we're going to dig into the open-closed principle in a lot more depth now. And so we're going to start with the definition. Now, this is a definition that comes from a book, Object-Oriented Software Construction, that was written by a guy called Bertrand Meyer back in 1986. And he says, A class should be open for extension but closed for modification. Awesome. I mean, what does this even mean, right? And so there are tons and tons of articles and blog posts and reports in journals or in magazines or videos, much like this one, explaining what the open-closed principle is. And of course, as we've seen with the telephone game and with Humpty Dumptyism, this thing has changed over time. So I've picked a particular recent example, and I'm not hating on the author of this post. I'm just using this as an example of how the open-closed principle is commonly represented in modern developer writing. So this is not an attempt to to hate on this author. This is an attempt to use their example as a reflection on what kind of current thinking about the open-closed principle really is. So we should strive to write code that doesn't have to be changed every time the requirements change. Well, from a kind of maintainability perspective, that seems to make some sense. If I've got my application that I've built and then some new requirement comes along, if I don't have to change a load of stuff, that's going to make my life easier. It's going to make it quicker to integrate this new requirement, like this new feature or this change in an existing feature. So that's going to make it quicker to get it to market. That's going to make it quicker to get the value of that feature to the customer. Continuously adding value for our customers is one of the top agile principles, so it sounds like we're doing the right thing, right? Or are we gold plating? Are we trying to future-proof our application by saying, right, I'm going to think of anything that someone could possibly want to do now and make it so that I never have to make any changes to get those things to happen? Because that affects the kind of value cost trade-off in a negative way. Because now I can't get my first feature out of the door until I've gold-plated it, until I've thought of every possible extension point, both relevant now and perhaps relevant in the future. Things that I think the customers might want at some point down the line. If I want my code to not have to change, then I'm going to have to do that work now. So I'm actually delaying the point where I get my first product, maybe my minimum viable product, or just the first thing that the customer wants right now, the thing that's going to solve their problem. I'm trading off more time now in order to have less time in the future. Is that really such a great idea? So let's look at the example that this author used. And the great thing about this example is that it's the example everyone uses. I think there should be some principle that says that articles on the open-closed principle are closed to new examples and open to plagiarizing the example that came in the last article about the open-closed principle. They all use this idea of drawing shapes or calculating something about shapes. Let me just take a step back at the moment and say to all of you, who are technical writers, who are bloggers, who do writing or talking about object-oriented programming, shapes are absolutely the worst example that you can possibly use, because the reality of shapes and the geometric classification of shapes, and then what you need to do if you're doing object-oriented programming with shapes are entirely different. So, hands up if you think a square is a rectangle. You see, there was a pause. There was a lot of, hold on, this is a trap, I'm not sure. Admiral Akbar was kind of climbing up behind you, going, it's a trap! And it is, you're right. Because a square absolutely is a rectangle. But I cannot use an instance of a square everywhere that I can use an instance of a rectangle, because a square only has one side length and a rectangle can have two, which means that from an OOP perspective, I need a rectangle to be a subtype of a square. If I want the Liskov substitution principle to work, if I want that I can replace instances of the parent with any instance of any child, then I need rectangles to inherit from squares if I'm going to have an inheritance relation at all. But we've all decided that a square is a rectangle, so now I have a circular dependency in my inheritance tree. This is a bad idea. Stop using shapes as your worked example. Anyway, what we have is someone has like a rectangle, and they have a thing that can work out the areas of a bunch of rectangles. And the way that it does that is to take a collection of rectangles and to work out the area of them all. Now, I want to generalize this to shapes. I've written a drawing tool that works with rectangles. People don't like really kind of just drawing rectangles all over the place. They want to draw some circles as well. So what I'm going to do is introduce a superclass that that has the ability to tell you what its area is. And I'm going to say that a rectangle is able to report on its own area. And now I'm going to change the thing on the right such that we are now, right, let's get all the way through the transitions. So now we're asking the shapes what their area are, and so if I've got like a circle that is also a type of a shape and a rectangle that is a type of a shape, I can still add all of the areas up. But so what we've done on the left does meet our definition of the open-closed principle. We've extended this thing by adding a new method, the area method, so it's open for extension. We didn't change any of the behavior in that class, or we introduced a new abstract parent, so we've only added. This is great. What did we do on the right? We rewrote the whole thing. So we modified one of our two classes in order to mean that the other one we only had to extend. So it doesn't feel like we've kind of we've got there. It doesn't feel like we've implemented this thing in a way that satisfies the open-closed principle, unless we just like blinker ourselves and go, no, totally rectangle, open-closed, rectangle, perfectly fine. Ignore that. Like we did it by getting this rectangle right. And like, what if I wanted to have the total area that bounded the collection of shapes, not the total area of all of the shapes? So now I want to think about intersection or overlapping. I would need to change this thing again. So we haven't protected ourselves from future requirements, which is what the author claimed the open-closed principle was about. Or at least, if we have, we've protected ourselves against particular evolutions in certain directions and not against evolutions in other directions. And we don't know what our customers are going to want in the future, and neither do they. So maybe what I need is a better expert. And I said that the solid principles were first kind of encapsulated in a single document by Robert Martin, so we'll try him. So now we have two primary attributes. Modules are open for extension. This means that the behavior of the module can be extended to meet the needs of new applications. Well, yeah, it's sort of compatible with what the other author was saying. We can see that we're being a bit more precise, a little bit more specific about what's going on here. They're closed for modification. The source code of such a module is inviolate. No one is allowed to make source code changes to it. That's pretty concrete, right? You know, we all can see that if you edit a file, you have blown it. You are no longer allowed to make changes to your modules. We can understand that. That's nice and easy. Now, I said that what we had to do was to think about who these people are and what they're thinking and why they're coming up with these rules. And this thing about not changing the source code at all for a module, yeah, that's quite a strict rule. Why would you come up with that? One of the reasons, this article was published in a journal called C++ Report. Now, hands up who's used C++? Got a few. Those of you who have used C++, how many of you are still waiting for your project to compile? Okay, so there's no hands, but there's a little bit of a titter, a little bit of laughter there, and that's because we all are familiar with the idea that like C++ compiles can take a long time, particularly if we're using metaprogramming and instantiating templates. It can take a long time to do a build. One of the things we get by saying you are not allowed to change your source code is that I never have to rebuild that module again, and I know that transitively anything that depends on it isn't going to need to be rebuilt because I changed the interface for that module, because I didn't change the interface for that module. I just told you you're not allowed to do that. So that's one of the benefits that this author is getting from the open-close principle, is that they're using a computer that they probably bought in about 1998, which is significantly slower than a computer from today. C++ builds are still incredibly time-consuming today. They would have been even worse on a 1998 computer. So they're saving themselves a lot of time and making their kind of debug and edit cycle a lot faster. So let's look at his example. We're dealing with shapes because there's only one example in all of object-oriented programming. And we've got squares and we've got circles, and we know how to draw squares, we know how to draw circles. Well, what happens if I want to draw something else? We tell the shapes how to draw themselves. So we've added the draw method to our shapes. They now know how to draw themselves. We tell them to draw themselves. So now we can handle any old shape. But what he then goes on to do is to show how successful this is by adding another requirement. And his requirement now is that they've got to be drawn in a particular order, so that when they overlap, we get the ones that are at the front drawn over the ones that are behind them. This makes sense. There are plenty of drawing applications that need this. I had to order a load of the objects in terms of depth in my Keynote Keynote slides in order to build this presentation. So we know that this is something that it is realistic for people to want. So we now have drawing all shapes in a particular order, and the way that we've done that is to introduce an ordered list of the shapes and then to pull the things off like a queue and then draw them. What you'll notice is that even this statement of the open-close principle, we've had to make, we've changed our thing. He said at the beginning, do not edit the source code. And we've now seen 3 different implementations of this one function. So it seems like he's editing his source code. Maybe I still need a better expert. Or maybe what I need to do is to go back to the original author of this principle and ask, what were you thinking? So you'll remember that the first pithy description, that a module is closed for modification but open for extension, came from Bertrand Meyer and his book Object-Oriented Software Construction. Well, it turns out it's much easier to understand what he was talking about if you read the 2 paragraphs that come after that description. If all you remember about the open-close principle is that first one, then you end up like Mr. Bean on that slide where he had no idea what he was looking at. But the thing about books is that books often have quite a lot of words in them. Yeah, I know. It turns out, right? And some of the words that are later in the book build on the ones that were earlier in the book. So we're going to look at those later words and see what we can glean from that. A class is closed since it may be compiled, stored in a library, baselined, and used by client classes. This is a long-winded way of saying released, shipped, right? We've given it to someone, they can use it. But it is also open since any new class may use it as a parent, adding new features. So then let's have a look on when a descendant class is defined, there is no need to change the original or to disturb its clients. So what he's saying is if I've got a thing and I come up with a new feature, I don't edit this thing, I don't add the feature there. What I do is I edit this thing, which he's using in inheritance, but the kind of delegates to it. And so I don't change the behavior of this thing. I adopt that behavior through inheritance or delegation, and then I add my new specific requirements or my changes down here. Now, the reason that I'm hedging over the word inheritance and saying or delegation is because I know that these days people don't like inheritance very much, and they say, oh, but I prefer composition over inheritance, and you're talking about inheritance, Graham, so I've now stopped listening to you. But inheritance is just a particular way of saying, I want the behavior of this thing in this thing. And the reason that we're kind of wary about inheritance and wary about its abuses is because there's a tight coupling between the parent and the child, right? If I change the parent, then that also changes the child. But I just said that you're not going to change the parent. So why is that a problem? Why am I still worried about changes in my parent affecting the behavior of my child if I'm telling you that you no longer need to change the parent? But, you know, feel free to use like other forms of delegation. Feel free to just say, like, you know, there's this other object over there, and I'm going to, you know, if I'm using like a dynamic language like Objective-C or Ruby or whatever, I'm just going to forward the message over to that object. Or if I'm not, then I'm going to write a load of boilerplate that, you know, that just rewrites the receiver of these messages. Like that, if that's what you want to do instead of inheritance, then that's totally fine. But also, what we're talking about is modifying the behavior of the original thing, which means that it does sound like these two things probably should be fairly tightly coupled, because we're saying that this thing is a variation of that thing, not that like it happens to use some of the same features, or that it needs like the same algorithms, or that it refers to the same data, but that it is a variant of that thing. So actually that tight coupling sounds like it probably is going to reflect what we want from this design. Anyway, choose to use inheritance or not. I'm going to follow the discussion in object-oriented software construction, and I'm going to talk about inheritance. So what we could have had was this. Let's once again use a shaping example, because, hey, I've run out of ideas too. But we've got a thing that can render rectangles and circles, and it does it like the original way. Then we've got a thing that can do all shapes. Now it turns out that like rectangles and circles being shapes as they are, a thing that can draw all shapes is like a more general version of a thing that can draw rectangles and circles. But a thing that does them in the right order is not a more general example. But the way that they work, the list of things that they take, you know, their inputs, and then the resulting behavior are still compatible. So each of these things takes a list of shapes, and actually outputs nothing, because drawing is like a kind of side-affecting change in this case. But we could imagine building a chain of core graphics commands, quartz commands, or a chain of instructions for a bitmap renderer on, like, you know, some other device, whatever. You know, so the input is a list of shapes, and the output is a list of drawing commands. These are all compatible, so we're not going to run into the problem where if I've got my thing at the top and I replace it with my thing at the bottom, my code breaks. It should all still work, but the behavior will be different, and that's what we want. Now, Bertrand Meyer had very specific opinions of what it meant for replace one thing with another and my code doesn't break. And this is a good time to go into that digression to see if we're still talking about the same thing. Because Bertrand Meyer was an advocate of design by contract. He was the creator of the Eiffel programming language, which makes it easy to write your contracts into your source code and then have them verified by your program while you're testing it and while your customers are using it. So what do we mean by a contract? Well, this is some slightly flowery language that I basically lifted from the United States Constitution, because it kind of felt contracty. It felt like a heavyweight commitment that would be made by people in big powdered wigs. And it says, like, the first paragraph we don't need to worry about, but it says, we hold these truths to be invariant. What that means is that there are things that in a module that you can say about the state of the world and of the module both before and after any operation that module exports. Except the constructor, because we don't know anything about the module before the constructor runs, because we haven't built the thing yet. And similarly with a destructor or finalizer, we're just saying, like, this thing is gone now, so anything that was true no longer needs to be true. But once you have built an object, before you use any of its methods and after you have used any of its methods, these things will always be true. Also, there are certain things that we need to be true before we use a method on this object. So, like, looking at those shape renderer functions, the top one only worked with a list of shapes where the shapes were circles or rectangles, right? So if I had a list of shapes that had a triangle in, that probably wouldn't do the right thing because it didn't know how to handle a triangle. Now we can express that in the contract of the class. We can say, if you give me a list of shapes and if everything in there is either a circle or a rectangle, then I will do my behavior properly. If you gave me something else, then that's your problem, not mine. I'm not going to code around every single programming mistake that you could make in calling my function. I'm going to tell you what you need to get right, in return for which I will guarantee that some things are right myself. So let's think. The top thing, the first shape renderer we had, could only do circles or rectangles. And then we inherited from it and built a thing that could render all shapes. So if I've got a list of circles or rectangles, I can pass it to this second thing because that takes any shape, and we've said that circles and rectangles are shapes. And in return for which, it will do the same thing. It will draw the shapes into whatever context we're drawing them to. So that means that the outcome, the post conditions of these things are exactly the same. The preconditions are more general. So we've gone from this thing can only contain circles or squares to this thing can contain any shape, including circles or squares, which means that it is valid, as far as Bertrand Meyer is concerned, it is valid for this thing to be a subclass, because the contract is at least as permissive as the original contract. And then when we added the ordered shape renderer, we just said, we're going to take the same thing and we're going to give you the same result, but we're just going to do the work in a different order. So we've made absolutely no changes to the contract whatsoever, and now we've still got the same thing. So armed with this knowledge, the open-close principle starts to make more sense, because it's saying the reason that you never change a class once you've released it is that you never need to. If you want to create different behavior or to extend the behavior somehow, then you build a new thing, using inheritance or delegation if you need to, that adapts the existing behavior and introduces the novelty, introduces the changes. And if you are going to inherit, then you do it in such a way that you can still use the child class if you want to in any context that you could have used the original class. So that is the world in which the open-closed principle makes sense. It's saying that, no, you never change anything once you've released it, but that's because you don't need to change it because you write your new stuff somewhere else. And this explains why semantic versioning sucks. Here's a semantic version. Do people use semantic versioning in their libraries? Do people use something like Node.js that pretty much enforces it, like npm or Ruby gems or CocoaPods or anything like that? So the first number, the big number on the left, the X, says this is a major release. Basically, I could have changed absolutely anything about this library except its name. And all you know is that you've got a thing that has the same name. It might have completely different behavior. It might do something entirely different from what the first version did. You certainly can't use any of, you can't rely on any of the API calls working in the same way they did before. The second version number, is the minor version, Y, says I've added stuff. Everything that was here before still works, and I have given you some new features that weren't there before. And the last version, the patch number, says everything that you are trying to do, all of the calls that you're trying to make, all of the API you're trying to use, has the same signature. So you can call this thing the same way that you could call the last thing, but I have changed the behavior. So what happens may be different. I think that we've now got to the point where we deserve the full-on triple face palm. Yes, because what's the easiest thing to deal with? It's adding new stuff, right? If I'm using like all of your API and then you add new API, that means nothing to me. I just get to carry on using the bits that I was using before, and there's some like dead code in my library that's added a bit of space to my binary. But what's also quite a bit easier to deal with is completely changing everything, because at that point I just give up. I just say, you know what, there's this new thing that doesn't work the same way as the thing that I was using before. I'm just going to think about whether I want to do things that way or that way. It costs me nothing to do things that way, but there might be advantages to taking things that way. I get to evaluate that. The absolute worst thing that you can do is pretend that everything works in exactly the same way, but change the behavior underneath me so that I don't know whether I'm going to get the results that I want out of your thing. And that's the thing that we've put all the way on the right in semantic versioning. So, the open and closed principle would tell us never make the sort of Z change. Y changes are free because you never see them at all. Like, you have to opt in to switching to this other module. And X changes, like, you just don't fit into this world. So, if you want to rewrite your thing, then just release a different thing. So maybe semantic versioning, like now that we've understand why we have contracts and why we have the ability to extend behavior without changing other behavior, maybe we should kind of think about, firstly, like let's just switch these two things, right? Because I don't care if you add new features. I can like asynchronously go and look and see whether they've got any value for me, but my stuff's still going to work. But I need to do so. I need to put some effort in if you're going to like make a patch change, because I now need to work out whether whether I'm relying on the old way of things working, and you've just silently introduced a different way of things working. And now let's give up pretending that a ground-up rewrite is a good idea at all. That if you're going to say this does different things in a different way, then I'm going to say, well, that's just a new library, and I'm going to decide whether or not I want that. But I'm definitely not just going to like adopt it because 4 is bigger than 3, or if you're Microsoft, because 10 is bigger than 2000. I think that works. So what am I saying? It's not really about the open-close principle. That was the thing that got you through the door. I apologize. It's about the fact that there are a ton of useful ideas. There are a ton of different ways to think about the work that we're doing and to learn from people who have been doing this before us and who have already come across some of the problems that we have. But just because we can adopt an idea doesn't mean it's going to be of benefit to us, because the context in which that idea arose may be different from the context that we're working in, and we need to be aware of how that person was thinking about their problem and what their problem was before we just go ahead and borrow their practices. And just because things get more complex over time, like as has happened with object-oriented programming and with MVC and with the solid principles, it doesn't mean that they're getting better or more sophisticated. It means that people are adding to them. Now, one great like motivator for adding complexity is when you want to give a conference talk, and so you've got to come up with something new that people haven't heard of before. So you attach your new idea to something that they have heard of, which makes them comfortable with it, and then you release that into the world. Now, the conference speaker has added their nugget of information. They've got their video out on YouTube. They've got their name on the presentation list and the brochure and everything, and they've made your world slightly more complicated. Go them. And honestly, I think this happened a lot with like object-oriented programming back in the 80s and 90s, when people started creating object technology consultancies and companies that would tell managers how to do object-oriented management. That was really a thing. I'm not making that up. There were object-oriented approaches to management. There were like object-oriented design companies. There were object-oriented development shops. Everyone knew that object technology was the thing that got you to the point where your invoice was on the manager's desk. And so they would add their thing to object-oriented programming in order to get that invoice there. But on the other hand, just because an idea is simple doesn't mean that it's like simplistic. It doesn't mean that it's naive. It could be incredibly profound. It could be that it works really well in a context that is different from yours. So I'm not saying like you need to go back to the open-close principle and adopt it the way it was originally written, and I'm not saying that you need to abandon it because it's like this bloated bad idea that doesn't work very well. I'm saying that it comes from a particular way of thinking about the work that you're doing. If you are thinking about things in a similar way, then it can work very well. If you're not, then let's try and think about those differences and reconciling them, rather than just blindly adopting the practices because they're the things that the famous people said. And with that, thank you very much for listening.